Okay, yeah. As said, I would like to first outline the presentation today. I will first answer the question, what is a brain-computer interface? And I will define this term, introduce the general methodology, and point up application possibilities. Then I will focus on currently available functional neuroimaging methods for building BCIs, and will introduce the two major sections here, namely measuring either neuroelectric or hemodynamic brain signals. And as the specific topic of this webinar is the use of fNIRS for BCIs, and fNIRS is a hemodynamic functional brain imaging method, I will then focus on BCI relevant characteristics of the hemodynamic brain signal. As a third point, I will focus on the fNIRS technique itself. I will introduce its working principles and practical and procedural aspects. I will also talk about the question, how can we encode information by means of mental activity that result in hemodynamic signals that we can later then decode. And finally, to evaluate fNIRS, I will list the main advantages and also some limitations in comparison with other functional neuroimaging methods. After this more practical part, I will demonstrate the feasibility of a multiple choice fNIRS-based communication BCI that we have recently developed here in our lab in Maastricht. And at the end, I will have some take-home messages for you. So what is a brain-computer interface? A brain-computer interface is a system which connects a brain, human or animal brain, and a computer. And it allows for controlling external devices through brain activity. That means without having to rely on a motor response, which is normally required for controlling such devices. BCI can also include a neurofeedback component, and that would allow a person to change actually his or her own brain activation into a desired direction. BCIs can be used for researching, enhancing, assisting, repairing or replacing cognitive or sensory motor functions, and in this webinar we particularly focus on replacing motor functions. So let's have a look at the general BCI methodology. So what is the basic design and operation of any BCI system? We measure brain activity by a functional neuroimaging method, for example fNIRS, fMRI, EEG, and then further process this activity or the signal to extract specific signal features, for example the brain activation level or a connectivity measure or any informative other aspect of the signal, which can be controlled by the BCI user and which encodes the specific user's intention. These features are then translated into commands that operate a device, for example a word processing program, a wheelchair or a neuroprosthesis. Okay, now let's switch to the second point, functional neuroimaging methods for BCIs. Actually, there are two different sections, I told you already. The first section is the section that is called measuring electrophysiological signals. Therefore, it's the electrophysiological methods or direct methods because we really measure signal coming from the neurons. And these techniques are electroencephalography, magnetoencephalography, electrocorticography, and intracortical recordings. The two last are invasive techniques. And then the second section is the section of the hemodynamic or indirect methods. Namely, here we obtain information about brain activity indirectly via the vascular or hemodynamic response to this brain activation increase. And here the two methods are functional near-infrared spectroscopy, the specific topic of this today webinar, then functional magnetic resonance imaging, which I will refer to also at several points. So now let's focus on the advantages and disadvantages of various functional neuroimaging methods in the context of BCI. Actually, in these tables, these pros and cons are listed with respect to several dimensions, and these I would like to introduce to you first. So resolution, temporal resolution refers to the question how fast can we measure brain signals. So it concerns actually the sample rate of a method, and of course the higher it is, the better it is. And as you can see here, because it's indicated by 3 pluses, the highest temporal resolution is for the neuroelectric methods visible. Then spatial resolution. This refers to the question, how precisely can we actually obtain the brain signal source? That means the location of the measured brain signal. And also here, the higher the spatial resolution, the better it is. And the spatial resolution is highest for intracortical recordings, because here we really put a needle-like electrode in a particular area, very tiny area, and we can record the signal. The other dimension, depth pervasion, which is called here, refers to the question whether we can actually measure brain signals of deep brain structures, and here fMRI is the most powerful method. Brain coverage refers to the question, how much brain tissue do we cover? Can we actually measure? And the more brain tissue we measure, the better it is. And also with respect to this dimension, fMRI outperforms the other methods. The last two dimensions here in this table, I think it's clear: invasiveness and mobility, and EEG and fNIRS score best with respect to mobility, of course, because they constitute quite compact systems. So I will not go through all these evaluations. You might have a closer look later, but the take-home message from this table is that every method has actually its pros and cons, and there's no perfect BCI method. One always has to consider the particular purpose of the BCI and choose the best suited method. Okay, so now I would like to look with you at BCI relevant characteristics of hemodynamic signals. So why do we focus on this, you might ask? I can tell you that knowing and of course then considering these is very important for building BCIs. Only then we can namely then get the best out of each of these methods. So the first signal aspect I would like to explain is the so-called hemodynamic delay. I have here prepared an animation, and imagine we present to the subject a short visual checkerboard stimulus, let's say of about 100 milliseconds. So, and using EEG, you would measure an immediate neuroelectric response. But using fNIRS or fMRI, we would observe a delayed hemodynamic response that is demonstrated here in real time. And the vascular response to neural activity, as you can see, it is very slow actually. So this considerably temporal delay constitute one actually not so nice BCI relevant characteristics of the hemodynamic signal, but it has to be considered, and then it can be maybe counteract. So let's now concentrate on a BCI, another relevant signal characteristic, namely the high single trial reliability of hemodynamic signals, and this is actually very positive. So here you see an fMRI signal time course evoked by a particular mental task, maybe motor imagery here in this case. So participants perform 16 trials. So what you can see here is the time course within, for example, the premotor cortex, and this time course is very consistent across time in that sense that these red periods here are periods where a subject performs a task. So shortly after the onset of this task, you see a strong increase in every single trial. This is very nice, and this is here summarized in this event-related average on the bottom of this page. Okay, so the next relevant characteristic is, I would say, it's the sufficient spatial resolution of hemodynamic signals. I have here a video that I would like to show you. So in this video you see that a participant performs different mental tasks: motor imagery, mental calculation, and inner speech. It's instructed, the subject is instructed visually. So you see here, for example, it's the resting period, there's no activation. Now during calculation, you see the brain activation pattern related to mental calculation, and finally inner speech. And in the end of this video, you will see all the three different patterns overlaid on top of each other, so that you see there is some overlap, but there's also considerable amount of tissue that is specific for a particular brain, for a particular motor mental imagery task. Okay, so in this slide I have again visualized the brain activation patterns. So these patterns are nicely differential, which is good for BCI purposes. One thing what I would actually already like to mention is, however, that the depth pervasion using fNIRS is limited. You see on the right side here that the head brain tissue from 3 centimeter deep up to 3 centimeter deep from the head surface seen is colored, and this is actually the volume which from which we can reliably measure activation with fNIRS, so the theoretical volume that we can measure. The nice info is when you look also on the left side that most activation is actually at the outer boundary of the cortex, so it should be within this fNIRS coverage. Okay, so now I would like to switch to functional near-infrared spectroscopy, more details about the method itself. Generally, as said, we indirectly measure brain activity via its vascular response, and for this we use near-infrared light, which has a spectrum from 700 to 900 nanometers. This penetrates in biological tissue, for example, the head and the brain. And actually 80% of the photons, they roughly follow a banana-shaped pathway from a source to a detector. So we have to place optodes on the head surface, and this is the source and detectors here. And on that pathway, the photons get absorbed or scattered. And the oxygenated and the deoxygenated hemoglobin in the blood, they have different optical properties, namely different near-infrared light absorption spectra, and this we exploit here. And we measure the different light intensities and the subsequent conversion that we can do to optical densities using the modified Beer-Lambert law. This help us to determine the relative changes in oxy and deoxygenated hemoglobin concentrations, and therewith we indirectly measure brain activation. And here you see the typical wavelengths that are used for deoxyhemoglobin and for oxygenated hemoglobin. Okay, so now I would like to focus on some practical or procedural aspects of fNIRS. First of all, nowadays fNIRS systems are quite compact equipment, so there are several systems on the market. What you see here is the NIRS Scout from NIRX, which is, I would say, the standard system so far. And what you have to do is to place sources and detectors on the head surface. The nice thing is that you don't have to use any gel. No scrubbing is necessary. Sometimes you have to remove hair below the optodes. What is also nice that you have some kind of flexibility in optode placement. For this, what you can see on the right side here, we have given montages for different brain regions. And what is also nice for measuring is that the subject actually can be placed flexibly also. It can lie, can sit, and this is a very good thing that there are no constraints. What I would also like to mention is that there are several physical features that are beneficial for fNIRS. For example, features of fNIRS participants. So for example, bright skin and hair color, and also thin and fine hair, as well as a short distance from the head surface to the brain tissue that we actually especially meet in children, is positive, because then you can measure more brain tissue, and also the light is not so absorbed by non-cerebral tissue. So this is just one thing. Okay, after placing the sources and detectors that you also see here visualized how they look like, we calibrate the system, and then we start continuously measuring oxy and deoxyhemoglobin changes. And the participant normally then runs or goes through a psychological or whatever experiment. Okay, so something else what I would like to mention, I talked about the fNIRS coverage already, so that we have a limitation here, but another limitation when putting optodes on the head surface I would like to demonstrate here. So imagine you want to record from prefrontal cortex, and you have a specific optode montage used. So this what is shown here in the NIRS coverage mask is what you can theoretically obtain, but not there are always spots in the setup which are blind, let's say, for fNIRS signal. So you cannot measure signal from source to source. So this would be blind. But by switching these optodes around, so you could get actually a signal from from this area. Of course, the problem is that we have no anatomical information about the subject, but this is maybe a good explanation why in some subjects you get good results, in some not. It might just have to do with a lucky or unlucky situation what concerns the output placement, well, what we have to live with, let's say. Okay, now I would like to focus more on the BCI aspect and look at the question, how can we actually enable patients to encode different informations or intentions into differentiable near signals? And yes, the best way is of course the direct encoding. So let's say you want to build a yes-no, simple yes-no communication paradigm, then you just think yes, and this can be measured, the response, and then can be decoded, and we can actually communicate. We are just thinking yes and no. I can tell you this is very, very hard, and therefore what has been done in the past mainly is an indirect encoding. That means we take kind of a deputy activity. So we do not use the natural activity, which occurs when you think yes and no. You use activity that we know from, this is very nicely differentiable from another activity. So for example, you use motor imagery, which activates a certain network of brain activation or inner speech for building this easy, simple brain-computer interface. Okay, so generally what we can do is we can exploit all kinds of fNIRS signal features. So what kind of signal features do we have available? The first is the spatial. This I think is already clear to everyone. This is by doing different kinds of mental activity. But also we can exploit temporal fNIRS signal features, namely, imagine we have a particular start of the encoding time window, and by asking a subject for each of the answer option, for example in this case here 3, to either start immediately or delayed, we get, because we have this nice single trial reliability, an early or a delayed response. And similarly we can also exploit temporal or magnitudinal features by letting a subject try to reach a high or low or medium level of brain activation. Okay, generally now we have to look at how can we actually get activation. The others was what kind of objective or let's say differences we can, quantification differences can we get. Here is the question, the second is that we have to look at how can we evoke brain activation. And first I said already we can evoke intentionally controlled mental activities, and here I have listed 4 groups that have been used already. For example, higher order cognitive tasks like mental calculation, covered language related tasks like inner speech or mental singing, and third, any mental imagery tasks, so for example motor, visual, auditory, tactile or emotion imagery, and also selective attention tasks can be used to evoke different brain activation patterns, for example visual, auditory or tactile attention task. And then the second form, which is more the automatic cognitive processing, that we really use brain activation that automatically evokes. About this you will hear a lot later in the second talk by Ujjwal. Okay, let me finish this section with listing the advantages of fNIRS as BCI technique. fNIRS is relatively low in price. Also the operation costs are low. We have a medium temporal resolution. The sample rate is up to 20 Hertz, but of course we have to consider the hemodynamic delay. So we have sufficient spatial resolution that I could show you. We have no vulnerability to electromagnetic environment. This is very good because this we have with other techniques like EEG and fMRI. Then we have also a relatively low sensitivity to head motion artifacts. Also this is with EEG and fMRI not given. We have no inverse problem. We really know where the signal comes from. The application is relatively easy, and also the mobility and the portability is a big plus. So for example here there's a system from NIRX, it's called the NIRS Sport system. Here literally you can put the equipment in the backpack, and then you can really do sporting activities, and by that you can measure brain activation. This is really very, very good. Let's continue. Generally the technique is harmless, non-invasive and noiseless, you know, with fMRI with a lot of scanner noise. And what we also have is a compatibility with paramagnetic medical equipment. So there are not too many exclusion criteria, if at all. So this is really great for really finding a high application range. Then a big plus is also we measure both oxygenated and deoxygenated hemoglobin changes. And therewith we have two dependent variables actually. This is a strong big plus. And the system is also compatible with EEG, fMRI, and TMS and TCS, so non-invasive brain stimulation techniques. And this means simultaneous measurements are possible, and this opens up a lot of nice application possibilities. Finally, I would also like to mention some limitations. The light scattering, of course, this is not good, and the absorption by extracerebral tissue we cannot control. So for example, the roots, the hair roots also kind of absorb the near-infrared light, so we cannot do something. And then, skin and hair pigmentation. Then we have a limited BEF pervasion, as we reach only surface layers of cortex, and there are still some practical limitations, I would say, but this is always so. For example, we have some quite heavy, might be quite heavy, the optodes, or especially the cables are quite heavy on the head after a while, so subject might complain after a while. So this is that's it. And now after this first more theoretical part, I would like to go a little bit more into practice. I would like to introduce the multiple choice fNIRS-based communication paradigm that we have developed in Maastricht. So this is an overview of existing hemodynamic communication, BCIs. So you see all kinds of communication have been realized for fMRI, yes-no paradigm, multiple choice paradigm, letter spelling paradigm. And in fNIRS we have already studies focusing on yes-no paradigms. So all these studies listed here, these are actually patient studies, and these are proof of principle studies. So the next step in developing the methodology would be to develop a multiple choice paradigm with fNIRS, and of course we start in healthy subjects here. So how did we realize the encoding? And we thought at that time, when we planned the experiment, that exploiting the temporal fNIRS signal features would be the best option. So what we did is we conceptualized a four-choice paradigm. So let's say options A, B, C, D. And what we said is that we have four different encoding times. So we have one trial, and this trial includes 4 different windows, and the subject is asked to perform a particular mental task. In this case it was mental drawing, early or later in this time window, depending on which answer he or she wanted to encode. Some words concerning the mental drawing paradigm. So we have very clear instructions to the subject, and what we say always is we use mental drawing because we think this is something that everybody should know and everybody should imagine, also a patient later. So what the instruction is please imagine drawing a simple geometrical figure such as a circle, triangle, cube, or a small contour drawing. With your right hand in a comfortable but consistent speed. Try to imagine using a pen. This might support your imagination. So this has shown in the past, evokes very nice the motor system in the brain. So how then is the answer encoding realized? So the subject is instructed auditorily. So we would ask a question like, what is your favorite color? And the subject would first be in a resting period for 20 seconds, and after 20 seconds the first stimulus would appear. In this case we have the question, what is your favorite color? The first option would be red, for example. And if the subject would like to encode red, she or he should start now doing the motor imagery task. And then after 10 seconds the next stimulus appears, namely green, and when subject wants to encode red and has started before with the encoding, now has to stop and just await the rest of the encoding trial. But so you see, after 10 seconds each, here another option is highlighted, and after the fourth option is highlighted, like here, after 10 seconds, then there is a command like stop, so that the subject, when encoding the last answer option, also knows when to stop the performance of the mental task. Okay, so in our experiment, we included 5 repetitions. That means 5 times the answer was encoded, and this was based on previous research. We started with a more conservative approach because we were not sure about how good will be the answer the coding accuracy, to have more flexibility later for an analysis. So here you see the expected ideal fNIRS responses. I mean, depending on whether a subject starts early or late, you see a shift of the hemodynamic delay, or the hemodynamic response here in this case. Okay, so what did we do? We measured 9 subjects. We had a first short training session of 25 minutes. The training was for training the mental drawing task and for training the answer encoding. And I can tell you it's quite easy. People easily get it, and so it took about 15 seconds. So then we also asked participants to fill out a questionnaire with biographical questions. And in the end, we selected 8 questions independently from another researcher not doing the analysis. Yeah, from these questions. And then we started then the fNIRS session, which took about 75 minutes, and we, okay, all this typical procedure. We placed the cap, which took 5 minutes. Then we had the localizer, 2 localizers, actually about 8 minutes per localizer, with 2 setups. And this was in order to kind of get better coverage of the brain. We just chose later the setup which worked best, where we could find the best channel. I will tell you something about in a minute, but just that you know, we measured our data with the fNIRS Scout 816 system. Here you see the equidistant optode positioning on left sensory motor cortex, because all subjects were doing right hand motor imagery. Okay. The next step after these localizers were time course inspection, and this was done because we wanted to select the best channel. So by using Turbo Satori, this is our online data analysis software which is developed by Rainer Goebel in Maastricht. This program nicely allows us to evaluate the data online, and then also has output like the T values of oxy and deoxy hemoglobin values, and the criterion to choose the best channel was based on the mean of oxy and deoxy hemoglobin T values. Why? Because we really wanted to make sure that we really measure brain hemodynamics. So it was really quite conservative. So you see in this case that channel S8D8 was the best because the mean is reached here the highest value. Okay, so the last part of and the most nice part of this communication set was done encoding the answer. So we asked 8 times questions to the subject. And here you see an example time course when a subject encoded the answer A. So what you see here is the 5 trials per run, and you see here very clearly the 5 single trial responses. And here the averages across these 5 trials. So the brighter the color, the earlier in time. So this is actually the moment when red would have been set, here green, here black, and here other. And again, you see here the ideal fNIRS responses, and you really see this is almost like textbook. The peak of the activation when you encode in the first answer period, which refers to answer option A, should be shortly after the onset of the next option, and this is exactly here the case almost in every of these 5 trials. And then what I wanted to show you also to convince you that fNIRS can be as good as fMRI data. So this is data actually from the same subject doing the same paradigm. You also see here that the signal quality is very similar. So if you are lucky, then things can look very, very good. Okay, this is decoding the answer by eyeballing, but this is not what we want to do because it's quite intense, maybe not in this subject, but maybe in others. So we also do analysis. We run GLM analysis of the best channels time course. We actually use the functions, the reference functions, according to the 4 different answer periods. And so, for example, here when we go back to our question, what is your favorite color? We have used channel source 8, detector 8, which refers to ventral premotor cortex, I would say, on the left hemisphere. So we would get, when plotting these means and also the separate oxy and oxyhemoglobin T values, we would get this plot, and it's very easy to derive that here is the highest mean value for the T value, and this it would be then the option for which we go, which is in this case red, the favorite color of the participants. So now here I present finally the common results of the whole experiment across our 9 subjects, but I also listed it here separately for the subject. So what you have to know here is here we do the multi-trial accuracy, which was derived online, and the single trial accuracy was then assessed offline. And what you see here, that the mean, let's say this is green, means that the first decoder option was correct. So the decoder again went, for example, for answer D, and D was correct. So this is meant by first decoder option was correct. This was in about 75% of the cases. Yeah, was it 75% of the cases. So the theoretical chance level is 25%. When we look at the single trial answer decoding accuracy, it's slightly worse, but this is kind of expected. But also here we reach almost 63%, which is a lot when you consider the theoretical chance level of 25%. And also we did permutation testing, and we could see that this accuracy was correct for 8 out of 9 participants. So that was, I think, a very good result. So let's conclude. I hope I could convince you all that fNIRS constitute a promising BCI method because of its non-invasiveness, harmlessness. It's really suited for repeated and frequent use, especially portability and mobility and the ease of use enforces applicability. The high single trial reliability can result in high robustness of the signal. I showed you many possibilities to build these BCIs because we can exploit fNIRS signal features very nicely. So this brings along a high flexibility, so there's high individualization potential, and relatively low are the costs when you compare it to other methods. So another point what I would like to stress is there is still high potential for further improvement of the fNIRS methodology, and this concerns to hard and software, and we are currently busy with this in Maastricht. But what my personal opinion is that fNIRS is really highly suited for clinical and daily life BCI